And on to electrons. The idea we have to start when we're thinking about electrons is we have to think back a little bit to J.J. Thomson and what he was doing with atoms. And remember what he was doing was he was applying electricity to them, and he discovered the electrons, because before J.J. Thomson they had thought that atoms were just hard spheres, that they were homogeneous. But really, when he applied electricity, he saw that they produced basically a current, an electric current. So there was electrons being knocked out of these neutral atoms. That was the essence of J.J. Thomson's experiment. What they found later was that they could do this with other types of energy. So this is an example of what's called the photoelectric effect. So just like it says, electric effect. So like it says, it has to do with photo, which we tend to think of as light, and electricity. So what they saw is if we hit this with wavelengths of light, if we hit it with, visible light, wavelengths of visible light. So what we're doing is we're shining visible light on a sample of metal. What would happen is that metal could kind of conduct electricity or start a flow of electrons, because electrons would be getting kicked out. Well, that looks really easy, right? You just shine some light, boom, we have an electric current. But that's not quite how it works, right? That's a little bit too easy. What we'll see with substances, when we look at the photoelectric effect on substances, is the amount of radiation that's coming in. Notice this is infrared radiation, which is really low energy radiation. When we hit, and it's not telling us what our sample is here, but if we hit a certain sample of metal with some infrared radiation, with some low-level let's say maybe radiation would be a better word, low-level radiation, we don't see any electrons emitted. We don't see that continuation of current. But if we get that energy up somewhere in the visible light, and the level of light really depends upon the surface material on what we're hitting it. So different materials you would have to hit with basically different colors of light. And when we think of colors, it's not important that they're different colors. What's important is that those different colors are different wavelengths and different energies. That there was this minimum, notice what it's saying here, threshold. And we'll talk about what these all units are in a little bit. But if we hit metals with this minimum threshold of energy, then we'd see this flow of electrons being produced. So this was the photoelectric effect. And then we were looking at what is this threshold energy and why is there a threshold energy? And if we went beyond it, then we could always get electrons emitted. So notice they have a particular example here. So it says the photoelectric effect in response to potassium. So it says potassium, if we hit it with 680 nanometers wavelength of light, we don't get anything. So that's like, notice as it says, that's in the red region. But if we get somewhere in the 540 nanometer region, which is green light, now we see electrons being emitted. So that's crazy. And then if we hit it with even stronger light, some blue light, we see even more electrons, or not necessarily more electrons emitted, but we also see electrons emitted. So that's kind of crazy. So what is going on here? Why are there minimum thresholds of visible light that is needed to eject electrons out of materials? And again, it's different for each material. Well, sometimes this problem is actually solved a little bit better looking at it from the other direction. So we're taking now a certain, notice a cloud of transparent gas emitting certain colors. So we're just taking any gas in a cylinder here, kind of, again, like J.J. Thomson did, and we're heating it up. Or it could be any type of energy. We're just adding energy. And it could be energy in the form of electricity or in the form of just a flame to this gas. And it gives off light, just like J.J. Thomson saw. Well, if we take that light and we run it through a prism, what we'll see is it's not giving off a full spectrum of light. It's not giving off every color. It's giving off specific beams of color, so specific wavelengths of light. So this is called an emission spectrum. So it's not giving off the full continuous spectrum, which would be all of our colors from red, orange, yellow, green, blue, indigo, violet. It is only giving off certain levels of light. Notice there's a red, kind of something in the greenish range and some more in the bluish range here. So why is that happening? Now, why are we getting a continuous spectrum if we hit this with energy? And if we hit it with more energy, what they found is we still get the same bars. It doesn't affect the amount of energy we put in or the temperature. It's not going to affect the emission spectrum that's coming out. The other crazy thing is, and again, this maybe is a better picture. Now they have hydrogen gas in here. They're heating it up. Again, they're just running electricity through it. It's emitting some light, running it through a slit in a prism. We're getting certain beams of light. So this is for hydrogen. Notice it's nice and clear. You have a blue, that green and red. So that was the same one we saw on the other page. But if we take different elements, notice they produce different emission spectrums. And again, these numbers in the bottom are representative of the wavelengths of light. So neon has a different emission spectrum than hydrogen. And if we look at other elements, we'll see different emission spectrums. Now notice this is what our continuous spectrum should look like, and we don't see that when we heat up individual materials, and it doesn't even have to be gases. Notice this is the emission spectrum coming from the sun, which is fairly continuous spectrum, but then we have hydrogen, we have helium, mercury vapor, some uranium here. Notice uranium has a lot of different bars of light, and we'll kind of talk about that as we go a little bit further. But well, what we find here that's going on is that these emissions are coming from electrons that are moving between energy levels. So if we have just a simple element here, and we hit it with this energy, and we're calling this energy of light a photon. A photon of light is a packet of light. It's a particle of light. So we have to think about light now as not a continuous wave, but we have to think about it for a little while. We have to think about that light coming in as a packet of light, a photon. And so that photon of light is coming in, that certain packet, that certain required amount of energy, and it's kicking that electron up to a higher energy orbit. So this is a lower energy orbit. A lot of times this is actually called a ground state, and this is called an excited state. And what we'll see is that these transitions for each element are unique. So this ground state, the difference in energy between the ground state, so this is change in energy, the difference in energy from the ground state to the excited state for every element is different. It's different. So it's unique, so it has a unique structure of where the electrons are around the nucleus. That's the one thing we didn't really talk about before when we were talking about atomic structures. We kind of left the electrons, they're outside the nucleus. But now what we're seeing is they're in orbits, and not just any random orbits that differ. They're in specific energy levels. So what these energy levels are things we can actually go in and calculate. Well, at least for simple atoms we can. So notice N1 is going to be what we call our ground state. This is principal quantum number 1, or this is called our ground state, our energy level 1, N equals 1. Well, if we have an electron in our ground state, and we'll just look at this series first. So they have specific names. Right now, that's not important to remember. But if we hit this electron with a certain photon of energy, we can excite it up to this excited state, energy level 2. Well, that's great and all. Where we actually get the wavelength of light is when this electron falls back down, it emits a photon of light that is equal to that energy transition. So that energy transition is going to produce a certain wavelength of light. And so if we can record these different wavelengths of light coming off the elements, what that's going to allow us to do is go back and reconstruct where those energy levels are, what are the different changes going on in every individual different element. Now, this is specific for hydrogen because hydrogen was the first one that was really mapped out because, well, hydrogen has one proton and one electron. It makes it pretty easy. And when we get into more advanced chemicals, you'll see that this type of model kind of, I don't want to say falls apart, but it doesn't quite work as well for us. So before we get into those actual calculations, let's just refresh for ourselves the electromagnetic spectrum. So this is the full electromagnetic, I knew I was missing some letters, magnetic spectrum, right? So we are talking about wavelengths that are in the visible spectrum, but the only reason we're focusing on those is because we can see them. Notice when we map out hydrogen's full emission spectrum, it has things that are in the infrared and things that are in the ultraviolet, things that we cannot see but that are occurring there. When we're looking at hydrogen, we're just seeing this little series in the middle, the Balmer series, and notice it is occurring for electron transitions between high states down to a ground state of 2, which again is not the final ground state of hydrogen. So we're seeing energy transitions from higher levels, 3, 4, 5, down into 2. Those are producing the visible lines that we can see, but notice there's a lot more going on and a lot more energy levels within that hydrogen than just the visible light. So we want to realize that if this is our visible light, and again, violet would be our most energetic, have our shortest wavelength. Over here we have our long wavelengths that are lower energy light. So we want to remember this. We want to remember electromagnetic spectrum and the ranges of energies and frequencies here. So notice what it's saying. Increasing energy, it increases this way across the electromagnetic spectrum. So violet is our highest energy light. Beyond violet is ultraviolet, which makes that pretty easy. X-rays and gamma rays. And so as we go this way on our electromagnetic spectrum, energy goes up, and so does frequency. And frequency, we're going to write, sometimes we'll see it as an F, sometimes we'll see it kind of as a V like that. Right now we'll just have it as an F. That also goes up. So higher energy electromagnetic radiation has a higher frequency, which means it has shorter waves. So our wavelengths are longer in the opposite direction. As we go in the opposite direction, then we go to the direction that we have longer wavelengths. So our wavelength, lambda is the symbol for wavelength, our wavelengths are getting longer. So infrared are longer wavelengths than red, followed by radio waves, which include TV and FM and AM radio waves. And notice these waves are huge, 100 meters long. These are 1 meter long waves. Notice most of the waves in the visible spectrum are measured in nanometers because they're so small. But notice if you get down to gamma rays, they're fractions of nanometers. Okay, so we have this wave. This wave has a wavelength, which again is the length of a wave from one crest to the next, or from one trough to the next, one full cycle of a wave. Now, what a frequency is the number of oscillations per second, or the number of waves we go by. It is not the speed of the wave. The speed of the wave would be following one point on that wave as it progresses through time, okay? Frequency is the number of waves that go by. And what we see is there's a correlation between a wavelength and a frequency. And what the correlation is a unit we call C. So our wavelength times our frequency, and I'll write frequency that way, or maybe we should make it as that F, since we're seeing it other places as F. Wavelength times frequency always equals C. And C is 3 times 10 to the 8th, or 2.9998 times 10 to the 8th meters per second. That is called the speed of light. So the speed of light is the speed of light, but it's not just the speed of light. It's actually the speed of all electromagnetic radiation. So notice, if the wavelength goes up, we get bigger. If we get bigger waves, then we have a smaller frequency. There's not as many waves coming by per second. And obviously, the inverse is true too. Well, now we're kind of feeling like we're getting off topic because we can measure those wavelengths of light. And this will allow us to have a frequency of light. We could calculate that. So how does that get us back to calculating those individual energy levels, those energy transitions that we're seeing in the element? Well, for that, we need another equation, and it's this. So these energy transitions between our excited states and our ground states. So again, when that electron falls down, that's when it's emitting this photon that has that certain energy, and that certain energy is equal to that transition. And what we can say for it is, if we go back and look at our graph here for a second, we'll notice that as energy goes up, frequency goes up. Our more energetic waves have higher frequencies. So what this equation is telling us is that energy and frequency, and here you'll notice they're using the V just to make it confusing, they're proportional. What H is a constant that makes them equal. So the energy transition within that atom is what's called Planck's constant times the frequency. And Planck's constant is right here, 6.6. Normally we write 6.626 times 10 to the negative 34th. They have it kilogram square meters over seconds. Normally we call it joule. So normally we call it joule seconds, and that's how we will use it. So frequency here is measured in seconds, or per second, seconds to the negative 1. We have Planck's constant in joules per second, and that will give us an energy in joules when we calculate it. So the big beauty of this is that, again, going back, we'll go way back here, is if we take a certain emission spectrum and we look at these wavelengths of light, well, we can measure their wavelengths. We can just get a spectrometer. We can measure their wavelengths very, very easily. Now we can take those wavelengths, and using this equation, we can convert those wavelengths into a frequency. Once we have a frequency, well, then we can plug it into this equation to solve for a change in energy. And again, what that change in energy is going to tell us is the electronic structure of the atom. We will know the energy transitions within that atom. We will know where those electrons are located. And what we find is they're specific. They're not moving around further and closer to the atom. They're at certain levels of energy, and there's certain energy transitions that are within that atom. So we're ending up with two wave equations here that we'll actually end up combining. So we have this one, which is that energy transition calculation based upon the frequency of light, and we know that frequency can be related, and this is giving a lot of different units, so it gets confusing. Let's call this C is the wavelength times the frequency. That's our basic wave equation. If we combine these two, you'll notice what we'll get. We'll get some combined units where the energy can be calculated straight from the wavelength. And we'll say it's Planck's constant times the speed of light divided by the wavelength.